for Chem 1 on heterogeneous mixtures. So a while ago, we did cover heterogeneous mixtures, and we looked at heterogeneous mixtures way back in chapter 3. And back then, we talked about heterogeneous mixtures as being a physical combination. Remember, not using the word mixture to define mixture. Physical combination of two or more distinct phases, where each phase could be itself a mixture, maybe a homogeneous mixture, or it could be a pure material like an element or a compound. And so this is where we're going to see exactly how these heterogeneous mixtures differ from the homogeneous mixtures that are solutions. So there are two main types of heterogeneous mixture. The first one is a suspension. A suspension, something like mud or a slurry of some sort. Many of the products or the results of reactions we've done in lab have been heterogeneous, have been suspensions. And the suspension is a mixture in which one phase, so remember we just talked about the phases, one phase can settle out, and when it settles out from the other phase, it basically separates. It goes down to the bottom. So think about mud separating out, settling down to the bottom. Think about medicines that you might have that separate out, or things in the kitchen, oil and water separates out, for instance. Now, one of the reasons they settle out is that the size of the distributed phase, so the particles, I shouldn't say just the distributed phase, the particles in the distributed phase is large. Now, when we say large, we mean large compared to molecules. So large is greater than about, let's put a little about sign down there. So greater than, let me rewrite that, greater than about 10 to the minus 6 meters, which is equal to 1 micrometer or micrometer, depending on how you pronounce it. So we're talking about things that are thousands of times larger than molecules. And so that's why we can say that they're large. When we have particles that large, the intermolecular forces that would work on them to keep them in the suspended phase are too weak. And so gravity pulls them down. The particles are too heavy, and gravity wins. Gravity pulls them down, and it separates them out, largest ones first, all the way down to the smallest one. And there's a video that I'm going to post along with this on how to look at how to see this, the time it takes for different particle sizes to settle out. These are going to be these heterogeneous mixtures. Anything that says shake before use. So, like I said, things like medicine, orange juice with pulp in it. That's something you want to shake it, otherwise all the pulp settles down to the bottom. And even if you like pulp, getting last glass that has like half pulp in it is probably not going to be something you want. The nice thing about these guys, and we said this before, but now we kind of understand, they can be separated by filtration. And so think of the copper 2 phosphate lab. Think of the aspirin lab, where we use the filtration and we separated out the, I guess we call it a slurry, where we had the product mixed in with the other liquid, and that other liquid was itself a solution that had some of the soluble products in it. So separated by simple filtration is usually enough to separate suspensions because the particles are large. The particles are larger than the pores or the holes in the filter paper. So suspensions are one kind of heterogeneous mixture, but they are by far not the most interesting kind. The most interesting kind is something called a colloid. Now, there's a whole slew of different colloids, and I'm going to ask to make sure you read this in the book because it does talk about some of the ways that colloids work, and they have a whole slew of the different kinds of colloids. And the different kinds of colloids, well, before we talk about them, a colloid is a mixture of one phase that's dispersed, and it's dispersed into another phase, but the other phase is called the dispersing medium, the other phase. In this, the dispersed phase, you can think of it like a solute, where the dispersed phase would be what's inside, what's been acted on, and the dispersing phase, dispersing medium, you can think of like a solvent. And often the dispersing medium is something like water, where you disperse a solid or something else through water. These can have solid liquid, gas liquid, liquid liquid, or solid gas or liquid gas. The only thing that you can't really have is a gas dispersed through a liquid or a solid. I'm sorry, you can have a liquid through a liquid. You can have a gas, a solid dispersed through a gas. Solid dispersed through a gas. No, there's one that's missing here. Liquid, liquid, liquid. Well, you can have liquid, liquid. 1, 2, 3, 4, 5. There's one missing. Gas, gas, liquid, liquid, solid, liquid. Oh, a solid, solid. And that's because solid dispersed through a solid is going to be something like an alloy. So we'll talk about the different kinds down below. I'll mention some of them down below when we get a better idea of what to look for. In these colloids, the particle size is a medium size. So it's between 10 to the minus 9 meters, which is 1 nanometer, and 10 to the minus 6 meters. So it's below that size for suspension, and when it gets lower than that size, the intermolecular forces are strong enough to keep the particles dispersed, as I said, because of their small size. And this is something that is going to be dispersed permanently. In other words, this would be something that you don't have to shake before using because those particles stay dispersed. So this would be something more like milk, which is a colloid. And the reason they stay dispersed permanently is because they're attracted. So the particles are attracted to the dispersing medium by their intermolecular forces. And so we're usually going to have polar or ionic, something polar or ionic on the particle that's going to allow it to be attracted to the liquid. These guys are a lot more difficult to separate. They're maybe not quite as difficult as homogeneous mixtures. You can separate them by using something called a HEPA filter. That stands for high efficiency particulate air. Now, most modern vacuum cleaners are equipped with HEPA filters because those HEPA filters can remove small dust particles, and especially if there's anybody who has allergies in your house, you're going to want to use these. And so it's going to filter particles that are less than 10 to the minus 6 microns, whereas a filter that we saw up above, the filters for suspensions are usually going to be around the 10 to the minus 6 meters or 1 micron size. Another way of separating them is something called a centrifuge. So a centrifuge is a device that you put tubes into that have your liquid in them. The tubes spin very fast. So the material, the centrifuge spins very fast, and it as it does so, it forces, it's like an artificial gravity. It forces the materials to have a density gradient, and the denser materials will settle out and the less dense materials will come to the top. And that's typically used for something that would separate blood. So blood is made up of a bunch of different materials. Blood is a heterogeneous mixture. It's a colloid, and you can use centrifuging to separate out the various components of blood. Now, telling these guys apart is pretty easy because suspensions will settle out. So as soon as you see something settling out, you know you can call it a suspension. How do you separate, how do you differentiate between a colloid and a true solution? And that's something called the Tyndall Effect. Now, you don't have to remember the name of it, but you do need to remember what the effect does. In the Tyndall Effect, colloids scatter light. And you've seen this before. This is like a laser in fog, the way that they, in spy movies, if they want to see how or in heist movies, you want to see where that laser light is for the security system, you spray a little fog and you can see the laser light. Otherwise, the laser light doesn't reflect off of anything. It goes right through the air, and air doesn't have the ability of scattering light. So in the Tyndall Effect, the particles are large enough to reflect the light waves. So the light waves actually bounce off of them. And there's a video you're going to see. I'm going to post this as well from the Khan Academy. That's pretty good at describing not just the Tyndall Effect, but differentiating between colloids, solutions, and suspensions. The particles are large enough to reflect the light, but not so large that they settle out. Because if they settle out, then they're not going to reflect the light. In fact, if you try, picture trying to shine light through a piece of mud or a piece of dirt, you can't do it because it's a solid. So you're trying to get light through a solid. So down below, I have a couple of images or a couple of diagrams here. On the top, I show a solution, and I'm showing a wave, a light wave. It has a wavelength of about 10 to the minus 7 meters. That's about 100 nanometers. Is that 100? No, 1,000, 100 nanometers, right? 100 nanometers. And the particles in the solution are too small. The particles are less than 10 to the minus 9 meters. And so what happens is, as the light wave comes by, this is a simplistic way of thinking about it, but essentially the light wave doesn't sense the particle. The particle is too small, and the light wave just bounces right, just goes right over it. It's like goes right through it. This is kind of the way that radio waves work in getting around buildings. Radio waves are long, tens to hundreds of meters long, and so they can get around buildings, whereas little light waves that are hundreds of nanometers, they're not going to get around the building, and that's why walls block light, but they don't block radio waves. Colloids, on the other hand, have much larger particle size, as I said, between a nanometer and a micrometer. And because of that, they're big enough here to block that light that tries to get by. And the diagram on the right, I've got two cuvettes set up, one with a solution on the left and one with a colloid. Now, this colloid is about a drop of milk in water. If you make it too concentrated, it's just going to absorb. It'll be like trying to drive through fog. By the way, fog, that's why we can't drive where there are high beams on in fog, is because the high beams will point up, reflect off the fog particles and back into our eyes. So it's not a laser, but it's the same phenomenon. So you see that as the laser light comes through, and the laser light's going from left to right here, and this happens to be a red laser. So the laser light's going from left to right. you can't see that laser light inside the cuvette. That little line there is actually the line from the back here, the line on the cabinet. But once that laser light hits the colloid, now the particles are big enough that they will scatter that light and we can see it. The whole idea behind the laser, by the way, is that it confines the light to what we call a coherent beam, and it keeps all the energy in that beam. If you saw the energy leaking out of the side of the beam, that means that you were losing energy. So we're losing energy as we go through the colloid, which is great if you want to see where that beam is. Not so great if you want that laser light to get where it's going. So some different kinds of colloids. We've mentioned a few: blood and milk. Blood is a liquid-liquid. Milk is a liquid-liquid colloid. Fog is a liquid in a gas. Water droplets dispersed through air. Dust is a solid in a gas. Jello is a liquid in a liquid, I believe. Mayonnaise is a liquid in a liquid. Butter is a solid in a liquid. That's why it's a little thicker. Marshmallow is an air. Is a gas in a solid. Foam is a gas in a liquid. And so all these things that you might think of as being kind of jiggly, but they're not really solids and they're not really liquids, most of those things that you can think about are probably going to be colloids. Again, you're not going to need to memorize or to know what the different types of colloids are, but if I tell you something's a colloid, you should be able to talk about it in terms of scattering light and in terms of the particle size and the ability to separate it out using filters or centrifuges. And we'll have some videos, like I said. All right. I hope you've enjoyed this unit. This is the last lesson of this unit, and we will be getting the review as well as the short worksheet on this particular lesson. All right. I will see you in class next time.